I'm Jehanzeb, and I'm a postdoc at SLS, Spoken Language Systems group headed by Dr. James Klaas. And I mostly work with vision language models, but but my area of research has been multimodal models in general for the last 3-4 years. Yeah. So today I'm. Oh, we did not stop the recording. Or we did. Yeah, stop. Yeah. So today I'm actually going to be presenting one of our recent books, which is currently under review, which is titled as GLOV, Guided Large Language Models as Implicit Optimizers for Vision Language Models. You can actually just read the paper here, and I can just go home. The paper link is there, but no, I will actually run you through the entire paper. So yeah, so let's quickly start, right? I mean, this is just a vanilla slide, which I just have to put for people who are not really into the vision language domain. This is just a basic representation of CLIP. So it has a couple of steps. First, what they did was that they basically just scraped the entire internet, your data, my data, from our Instagram pages. And basically, this is the paired data. So you have the images, and then you have the paired captions with it. And how is this network trained is super simple. So you have the captions coming in through the text encoder. You have your images of this cute dog coming in through the vision encoder. You get your embeddings, and then the objective is basic contrastive loss. So basically, we want to match or we want to pull closer the embeddings of the image and text pairs which are related, and then we want to pull apart the embeddings which are not related, right? So quite simple. So, but they do it at scale, and yeah, this is how it works. But what the authors basically found was that they could actually use this as a zero-shot classifier as well. So, for example, here, how do you actually use their pre-trained network or pre-trained encoders as open vocabulary classifiers is super simple. So you have let's say we have a bunch of images, and we kind of already know what they could be, but we don't exactly know the ground truth, right? So, for example, we could just embed the entire vocabulary space, whatever we have in this world. We can just embed it through the text encoder, get our embeddings, and then let's say we have a query image, and and now we can also get the embeddings for this query image. And now the task is super simple. We just need to basically find the closest embedding to our text embedding, right? And then whatever is the closest, which is through simple cosine similarity, we just say, okay, so this is the class, right? Okay, so now we all know what are vision language models. This is one type of vision language models, which I would be calling as dual encoder vision language models. Later, we would also be discussing encoder decoder based VLMs, but that comes later. So anyway, so there are plenty of ways in which we can actually make or construct these zero-shot classifiers, right? So again, we have this wonderful image of a flamingo. We embed it through the vision encoder. Let's say we have these embeddings, right? And now, as I said, that that there are plenty of ways. So one way to build this classifier here is to basically just embed the class names itself, right? So for example, you can just embed the class name flamingo, right? And then you can basically do again a cosine similarity matching between the text embeddings and the vision embeddings to find your correct class name. And then you have another way, which is slightly better way. For example, the original CLIP paper showed that if you don't do this, which is basically just a simple class name, but you do a photo of a class name, then you basically get a little bit better performance, which is somewhat like 1.4% on ImageNet, which is quite a lot actually. And an even better way to do it is to kind of use these kinds of set templates. For example, a good photo of a bad photo of a blurry photo of a blah, blah, right? So they basically give us a list of these prompt templates in which you can just replace these class names, and then you can actually get a substantial boost. For example, it was, I think 2% on ImageNet, which is again quite a lot. And this is kind of the boost which I'm talking about. These are the results on ImageNet. So this would be with this classifier, this would be with this classifier, and this would be with this classifier, right? So, okay, but where's the problem? The problem is that these templates were handcrafted. So, for example, a good photo of a bad photo of a, etc. These were handcrafted. So, somebody sat down, maybe it was Alec Redford himself, who sat down and basically wrote these templates, right? But now, in this age, we basically want to move away from this handcrafted templates, right? Because we have tools which are, maybe you've heard of them, large language models, right? So here we come to our first problem statement, which is that, sorry? I need to connect. But isn't it already recording? It's recording. It's recording. But how do I connect to the Zoom? Just enter the Zoom. Yeah, MIT. Wait. Now this is my work. There's a MIT for that. Yes. I don't know. What is the link? Do you have the link? Already connected. It's Slumber. MIT Zoom seminar. MIT. Yeah. But this is signing, right? No. It's okay. It's okay. It doesn't matter. What does it matter? I can present it again and we can. So anyway, so now coming back to the problem statement number one, right? There would be two, by the way. So can we replace a human, or at least, I mean, I will be a little bit, careful in saying replacing, but I should rather say, can we pair an LLM with a human, right? To help it to kind of come up with these handcrafting or to go away from this handcrafting of these templates, and can we actually frame this prompt search as an optimization problem? So yes, we can. Spoiler alert. But let's say so just to give you a kind of an inspiration, or the inspiration from this work comes from this iClear 2024 paper, which actually used large language models as optimizers for natural language tasks. So here, the overall framework looks somewhat like this. That you have an LLM, and you basically just run it in a loop, and you basically want to find better prompts for your downstream task of interest, which could be mathematics, for example. And you have this objective function, or this objective evaluator, which is basic accuracy scores, let's say. And then you have these scores, and you basically meta prompt the LLM in a loop to kind of enhance the accuracy on your held out, let's say, train set, right? So how can we actually directly just apply this for these vision language models? So here is the vanilla version of the approach, right? This is the first version, by the way. So here, what we do is, so LLMs as optimizers now for VLMs. So what is actually happening here? Now again, we have our friend LLM here, and then what we want to do is that we want to pair two disjoint models. One would be this VLM, which is again a clip. This is the LLM here. And then we want to basically prompt the LLM in an iterative fashion to come up with better prompt templates, right? And how is this being done is through this LLM prompt, which basically contains some system instruction, some task description, and ranked in context examples. I would explain what exactly are they. So this is how the optimization procedure would typically go. So we just basically ask the LLM with some or provide the LLM with some description. For example, the task is to kind of classify photos of cats, right? And then we want the LLM to give us these prompt templates, which we were basically talking about. We would ask it to get to give us n prompt templates, for example, right? And then let's say these are the prompt templates which we get. Now we just basically want to embed them. We of course want to add our category name of interest. So the LLM basically gives us these placeholders because it is instructed to do so. And then we just basically replace these category placeholders with the actual class name. We run them through the text encoder here. We have our vision embeddings here. We just do a basic cosine similarity matching, and this is actually where the ranking is going on. So, for example, we have these n prompt templates coming in. We have a held out train set, which is just a basic one-shot train set, train data. So basically, one labeled example per category. And now we just basically want to find the fitness or the purity of each of the prompts which was being generated by this LLM at each iteration step or at each optimization step, right? And now these prompts are kind of are actually fed as ranked in context examples. So by in context examples, I would ranked basically means that we provide the top end and the bottom end prompts to basically instruct the LLM or to kind of give it some notion that these are the kind of language patterns which are being preferred by my downstream VLM, because we have to remember that this VLM is not really connected to this LLM in any other fashion other than these in context examples basically. So yeah, so we run it multiple times, and the objective is to basically improve the fitness or the classification accuracy for my downstream data set. Okay, so this is the LLM prompt is basically inspired from my previous work called meta prompting, which basically, or it is kind of inspired, but we kind of do some substantial changes to it. So this is how it would basically look like. You are provided with a dataset name, description, top K and bottom K, best and worst examples, and then there is a task description here. Your task is to provide me with n number of new prompts. This is for the so we basically do it. So we basically generate one prompt in each call. So basically, it's running in a loop. I would tell you why we are doing greedy sampling here, because the next part of the paper actually would motivate this. But anyway, so this is kind of the overall setup or this LLM prompt. But yeah, I mean, there is one thing which I might have forgotten, right? Which is this guidance, right? Because in the name of the paper, we call something like guided large language models. But currently, I just kind of went over the optimization procedure or how to use large language models as optimizers for VLMs, right? So what exactly is this guidance? So this is where I come to the problem statement number 2. So can we guide the prompt generation process towards the notion of goodness? Or the notion of goodness in this sense, in this case, is basically the natural language pattern which is being preferred by my downstream VLM. So can we actually explicitly guide the language generation process in each optimization step towards this goodness or this effectiveness? So I mean, we can, but yeah. So to kind of give you a little bit of a context, this is a field in NLP, which is basically steering the language models generation towards something, right? So there is a paper called ECTAD. What it basically does is that it has these two prompts. One prompt is I love talking about weddings. Maybe it's considered as a good prompt. And this is like kind of considered, I hate talking about weddings, bad prompt. I don't know. It depends on the context, but but this is the example which they provided in their paper. And then they just basically embed it through the network. They have activation 1, activation 2. So this is the steering vector which they generate, which is basically the difference between these two embeddings, and they just add it to the LLM for the next generation step. So what they are basically trying to do is that they are trying to steer the language generation towards some portion, or towards some setting, right? In their paper, they show that this is actually super helpful for reducing hallucinations. Um, but we actually do it for some completely different thing. So now coming again, now we have the complete method GLOV, and you must have seen that we have also added some new things here. So this is where the guidance is actually happening. So for example, as I told you that we already know the purity or the effectiveness of each of these prompts which was being generated in the previous steps, right? So now we actually know what is the effective prompt and what is not an effective prompt. So now we kind of have some ground truth measure of where to guide the LLM, right? So how do we do it? We just basically choose a better accuracy prompt. For example, in this case, this is the better accuracy prompt giving me 52.1% accuracy. This is the lower accuracy prompt giving me 47.2% accuracy, which is actually so this accuracy comes on the held out train set, which is this one-shot train set. Yeah, so now we just have to kind of get these sentence embeddings. I should again be a little bit careful. These might not be sentence embeddings, but because we just pass it through the LLM, and we take the intermediate activations from the middle layer, in this case llama 3, yeah, so we basically have these H positive, which is sentence embeddings for the positive prompt, H negative sentence embedding for the negative prompt. We just take a difference between these positive and negative, scale the difference, and then we just add it autoregressively for the to the last token of the LLM for the next generation step. So I mean, intuitively, the intuition was to kind of move towards the towards the notion of goodness, or towards the language patterns which were giving us higher accuracy. Um, yeah. Yeah. So basically, this is what is happening, and for each newly generated token, this steering vector would be added, which would be a scaled, which would of course be scaled by this alpha here, and yeah. So we do it for like uh, multiple steps, and this is actually what how does the optimization look like? So yeah, on the top it is the dual encoder models, CLIP, VITB32. This is the encoder decoder model, Quen to 7 billion. I would actually come to the encoder decoder models in a while, but on the y-axis is the top one accuracy on ImageNet held out train set, and on the x-axis is the optimization steps. We limit the optimization steps to 25 because it takes forever to run, for example, these Lava 1 vision. So blue would be the GLOV without guidance, and orange would be the GLOV with guidance. So we basically see that that our guidance is actually helping as the optimization is proceeding. Anyway, so yeah, as I promised, so just to give you a little bit of a context of the decoder-based VLMs, as the name suggests, they have instead of having dual encoder, they have one encoder, which is the vision encoder to kind of encode the images, and then they have a decoder, which is a language model, for example, your favorite language model, maybe, I don't know, Llama 3, let's say, and yeah, so they basically project the vision space to the language space, the input the vision tokens after the projection to the language model, and this is how they enable these networks to do vision processing, basically, right? So yeah, So this is actually a huge line of work which was popularized by this paper, visual instruction tuning, presented in Europe 2023. Anyway, so coming back to our work or some results. Of course, this is the favorite slide for any researcher, because you have to show your bold numbers. Anyway, so yeah, so this is the image classification results on CLIP. We can see, for example, for the large scale ImageNet, it helps quite a lot. Actually, on all other datasets as well. These are some language or the actual natural language prompts which were being generated. For example, this was actually a super interesting case for the aircraft dataset. You will see, for example, they have these artifacts inside their inside the prompts, right? These artifacts, I could never think of them, but I actually tried to remove them myself and try to see what happens. And this was actually decreasing the performance for this particular data set. So the point is that that our method automatically finds the natural language patterns which are being preferred by the downstream VLM without us, or they might not be super intuitive to us humans, but somehow they are intuitive to for example, CLIP. Okay, so results for Lava 1 vision, we see particularly huge gains. For example, for the large scale ImageNet and for Stanford Central Cars dataset. Yeah. So this was, yeah. So these are a couple of prompts which were being generated by the model. Yeah, can you identify the specific aircraft model or subcategory, blah blah blah, and for example, it also comes with a very verbose prompt for food data set. Yeah. So, but somehow these prompts help the model for classifying the images in the data set correctly. Yeah. So we also tested it for safety enhancement, where the task is that the model is being provided with some unsafe instructions, and the model has to basically reject these unsafe instructions, which can be anything. Yeah, we find some automated prompts, and we see that so these splits would be lower is better, and the last thing would be actually higher is better. So yeah, so we tested on a couple of data sets, and these were yeah, some good results highlighted here. This was the initial prompt from which we started our prompt optimization. This was GLOV without guidance, and this was GLOV with guidance. Please carefully scrutinize the following instruction, etc., etc. So yeah, it actually generalizes to other tasks as well. We tested here MOLMO as well, which is a recent VLM decoder based again. Yeah, so just coming quickly because I'm running out of time as well, towards some ablation studies which we performed, or how did we actually choose the layer for guidance. This was done through a couple of experiments which kind of showed some correlation. So so here on the left we linear probed different layers in Llama 3 for the sentiment classification task, and we found that the middle layers were kind of giving us better accuracy. So yeah, so this kind of hints that the middle layers have the ability. I mean, yeah. The middle layers can give us actually semantically meaningful sentence embeddings, although these decoder type VLMs are not really suitable for this particular task. But yeah, it kind of hints towards this at least. And then there's this ImageNet accuracy, which we kind of ran a sweep, and we found that for layer 16, 17, it was actually also giving us the best accuracy here. Yeah, so this is how we chose actually the middle layer, which is the layer 17. yeah, for this guidance in our work. And then there are some interesting ablations where we actually reduce the number of images for calculation of this purity metric. So, for example, in the in ImageNet, there are 1,000 there are 1,000 classes. So 1,000 images would be the complete set, and then we just basically decrease the number of images. This was super surprising for me as well when I was running the tests. That the performance was not decreasing as much, or at least it was better than the baseline numbers here, even by just using 10 classes. Uh, so this could probably mean that our data downstream data sets are kind of similar in nature. Yeah, so it kind of finds some general prompt which can actually generalize to other classes as well. Uh, in the paper, we call it as a sub-shot experiment, which is basically even less than one shot. Here on the left, the same experiment done for image and rendition data set. Yeah, so we also scaled the LLM size. Uh, there is some performance improvement, but not exponential, I would say, because here we increased it 10 times, 10x, so from 7 billion to 70 billion. Um, yeah, so this also kind of hints that our method might scale with better LLMs. Um, then this was actually a very important experiment where when we add the safety instruction or the safety prompt, then the model should not actually decline to answer journal or decline or decrease its performance on journal purpose benchmarks, for example, SEED and MME. Um, and actually, what I found was that in one of the configurations, the performance was actually increasing by adding the safety instructions. Of course, it's also decreasing in other configurations, as you can see. But this was kind of interesting, which maybe hints that the actual safety instruction is kind of instructing the model to look at the question quite closely, which induces some good properties into it. Yeah, I don't have an exact answer for that, but these are the numbers which I got on this MME benchmark. Okay, so this is the prompt evolution. We start with at step 0. We start with the photo of A on the left. This is the GLOV with guidance, of course, and this is the without guidance GLOV. Yeah, so there were a couple of interesting things here. I just kind of skimmed through the number of steps. So for example, at one point step, our GLOV is or the guidance is finding that this particular artifact, which is enclosed in these brackets, square brackets, is helping the model somehow, right? And then we see that it's kind of sticking to this particular artifact later on as well. So, but here on the left, on the right, we can basically see that it's not really sticking. So although these kind of artifacts, human might not put them directly, but they were induced through this guidance methodology which we applied. So just to quickly wrap up, I presented a prompt optimization method that pairs two disjoint generative models, a guidance scheme as well that constantly drives the optimization towards a notion of goodness. Then we extensively ablated and evaluated multiple VLMs on different tasks, showing generalization on two X's, and extensive ablations studying the different design methodology. The paper is here on arXiv. Maybe you can scan it, and if you're interested, and if you have any other questions, so you can also go ahead. Thank you so much. Yeah.
can you elaborate a little bit more on how you rank it and what you think might be like, because it seems the ranking is very important.
Yeah. So ranking is basically done on this one shot train set, right? So for example, this is basic accuracy. So we just evaluate each of the prompts which are being generated at each step, right? And then we have a associated accuracy with this with each of the particular prompts, and then we can just rank them in ascending order or descending, whatever. And then in the next step, we just basically provide the top K highest performing prompts and bottom K lowest performing prompts as in context examplers to the LLM basically, right? And we just run it multiple times and basically to kind of tell the LLM what kind of natural language patterns are being preferred by my downstream VLM there. So yeah, it's actually quite important. Yeah, so this is how actually it's done. Okay, I'm short on time as well, so maybe Limin can come. If you have more questions, I'm happy to answer them later.